everyone. We're going to start a new section today. Essentially, we're going to be looking at an application of integration. We're going to try and find a method or discover a method for finding the area between two curves. So, take the simplest situation and build from that. Imagine that you have two functions. Let's call the first one y equals f of x, and the second one is y equals g of x. And this guy here is x equals a. Say this guy here, oops, yeah, that's not it, is equal to b. And we would like to find what is called, not reasonably, the area between two curves. Right, I'd like to know how many square inches of material that would be. Right? So what we need to do here, well, we don't need to, actually I'm going to tell you that there is a way to do that. So here goes. To find the area between two curves, you use this formula. It's the integral from a to b. That seems reasonable, right? You're starting a and you're finishing at b. Any guesses what I'm going to write down?
We're going to do f of x minus g of x.
Wouldn't that be nice if that's all you needed to do? Agreed? And that's all you need to do. Now, as long as it's a simple curve, right, there's no weird stuff going on. A single curve always on the top, another curve always on the bottom. Then the top curve, take away the second curve, subtract them, and find the integral of that, and this will be the area of this fella here. Now, a couple of things that are kind of guaranteed, and you must make sure that this is true. F of x has to be bigger than or equal to g of x, right? In other words, f of x has to be up high, and g of x has to be down low. Seems reasonable. Also, when you use this formula, the area is guaranteed to be positive. Do you know that sometimes when you find the area under a curve, the answer can be 10, it could be 0, or it could be even negative 10, right? All of those are possible for a single integral. But for the area between two curves, the area is always going to be a positive answer. If you ever get a negative answer to this question, then you've done something wrong and go and figure out why. In this context, that is a physical area. So it makes kind of sense that it's like a real piece of material that it really should be positive number, right? It wouldn't make sense otherwise. So we're going to look at the process for how you do these, and then we're going to make them gradually more awkward and more difficult. So first one is, let's put some stuff in it. So suppose I have a function. Oh, who am I going to call? Call this guy f of x, and it's x squared plus 3, so I guess I could put that in. Okay. And then I have a second curve. It's going to start here. And it's going to go down this way. I'm going to call this guy g of x. And g of x is going to be, oh, what shall we make g of x? That's a good question. What will I make g of x? Make g of x 7 minus x squared. And let's assume that we're being asked to find that area between the two curves. Now we have a nice formula for doing it. It's from the start to the finish. Top curve, take away bottom curve. So f of x and g of x aren't written in stone. F of x just means whatever the top one is, and g of x is whatever the bottom one is. So when I do this fella, and I want to find its area, I need to do the integral from, oh, well, that's easy, 0. Wait a minute. Don't I need to know the second number? So can you see that sometimes you may have some extra work to do? How will I find the x coordinate of that number?
When f of x equals g of x?
Okay, so if we solve when is f of x equal to g of x, we are going to get x squared plus 3 equal to that guy, right? Which is why I was posing a little bit. I was hoping to make something nice. If you add an x squared to both sides and you subtract the 3 from both sides, well, it's not as nice as I want, but it'll do. Don't you get x squared equals 2? And then if you take the square root, technically shouldn't you get a plus or minus root 2? But can you see in this picture, it's pretty obvious that this guy is root 2, right? The negative root 2 would be over here somewhere. So we now have that bit done. Now, according to our formula, it's f of x take away g of x. Now, if you just use that like a formula, you're going to come undone sometimes. This black curve is f of x. This green curve is g of x. So which one goes first and which one goes second? Is it this guy, take away that guy? Or is it that guy, take away this guy? Because one of them's right and the other isn't.
G of x take away f of x.
Okay, so in this case, it's 7 minus x squared, take away the x squared plus 3. So I don't want you to think of these as f and g. It's much better to think of this as top one and bottom one or something, right? In fact, in a lot of the questions in the homework, they put in a funny little rectangle that looks like this. And what this rectangle is meant to do is, can you see the top of the rectangle is the green guy and the bottom of the rectangle is the black guy? It's just a way of getting you to visualize who's high and who's low. Now, here's another thing which you can sometimes not pay attention to. Do you notice its first curve take away all of the second curve? Now you may think, what's the big deal here? This is the wrong way to write this fella down. Top guy, take away the second guy. Now you look at this and you look at this and they may seem superficially that I've written the same thing, but I haven't, have I? You realize it's first curve, take away second curve, right? That means you take away both pieces. Do you see here I've only taken away the first piece and the second piece is left alone. That's a common mistake. So it's now going to be the integral from 0 to the square root of 2, 7 take away an x squared, take away an x squared, take away a 3. That's going to be the integral from 0, square root of 2, 4, take away 2x squared. We comfortable with that? Okay. The 4 becomes 4x. Add 1 to the power and divide by the new power. You get that. You have it from x equals 0 to x equals the square root of 2. And what does that give me? Well, it gives me 4 square root of 2's, take away 2/3 square root of 2 cubed, minus a whole load of nothings. That gets me 4 square root of 2's. That guy there, if you simplify him down, there's a couple of ways of looking at it. You get the same answer in both situations. You can think of the square root of 2 cubed as being the square root of 2, square root of 2, square root of 2. And if you look at it that way, you get that as your answer. You can also think of it as the square root of 2 cubed, which is the square root of 8, which also gets you that guy. Do you see? It doesn't matter. You see it, because some people see it, one way, and some people see it the other way. So that's 2/3 times 2 root 2. So that's 4 root 2, take away 4/3 root 2. I should really be able to combine them, aren't I? So that's 12 take away 4, so that's that fella. There's your area. It does have a flow to it, doesn't it, this process? You might not need every single one of these lines. I put in every line I could think of. Now, the first one I gave you had a nice picture, which certainly helps. I suggest that if there isn't a picture, you draw one anyway. So suppose we gave you this question. So the question says, find the area between y equals x cubed and y equals x. Not an awful lot in that question. That's it. So if you want to find the area between these two things, step 1, draw a picture. If you don't know what some looks like, put it in your calculator. If you do know what it looks like, you can draw it. Now, if I go into this calculator that I have and I type in x cubed, and then I just put in x, and I don't really know what my window is, but I'm going to do -2 to 2, which seems reasonable. If I do a zoom to fit, there's what x cubed looks like. There's what the square root, there's what x looks like. Now that I've seen that, I'm going to go down and change my window to -1.1 and +1.1 and zoom to fit. There's x cubed again. There. Do you see? I get a gist of the picture. So all I basically done there was change the x up here. So I know that y equals x cubed looks like that. Right. And I know that y equals x looks something like that. And we're being asked to find the area between these two curves. A lot of these area between curves remind me of bananas, boats, and eyes. They all seem to have that kind of look to them. This one here looks like a banana to me, but it might look like a boat to you, but that's fine. That's step one, draw a picture. Now step two is coming up. Don't we need to know a start and a finish for this question? We need to know a value of x, which is essentially going to be here, and we need to know a value of x for here, right? So that's going to be step two. Find the x coordinates of the intersections. Now, someone already told us how to do that. Don't you set f of x equal to g of x? You put one curve equal to the other and see when are they equal. Because when they're equal, won't it be these places? So in this case, we're going to have to solve when is x cubed going to meet up with the straight line x. So when are they equal? Now, when you solve equations, you have to be a little bit careful about how you solve them. So I'm going to show you two ways to solve this. One of them works and the other doesn't. All right? Okay, here goes. Subtract x from both sides. What do you think I'm going to do next?
Factor out maybe.
Okay. X squared minus 1. Can I do some factoring with x squared minus 1?
Doesn't that turn into x plus 1, x minus 1? Sorry.
Yeah,
That's
you're good. It's a little bit different in Zoom. In a classroom, you'd see other people around you and you know you're about to speak or if someone else is. Now, that tells me that there are 3 places where those guys meet. And this is the good way to do it. -1, 0, and 1. Would you agree I could probably guess the 0 just looking at the picture, right? Now, over here, this is the wrong way to do it. Oh, I know what you can do here. I'll divide both sides by x. And that will get me only 2 of the solutions, but not the one in the middle. Correct way? Wrong way. Why is this correct? Because it gets you all the solutions. Why is this wrong? Because it loses or misses one. I mean, they share a lot of the answers, but they don't share all of them. That's the problem. Stitch 3 coming up. I'm calling this find the integral order. Right. If you look at this picture here, if I draw one of those little rectangles, just randomly somewhere, in this case here, do you see the green line y equals x is high and the black curve x cubed is low? Right? That the green is high and the black is low. Well, that tells me that if I want to find the area, it should be x, the green one, which is high, take away x cubed dx. You agree? Now, where should I start and finish? Well, that's where the problem is. If you look, I know my shape's not quite to scale, But once you get from 0 to 1, isn't the green always high and the black's always low? But what happens if you go from -1 to 0? Don't they switch places? Which means that this fella is only good for that guy. So if I find this integral, won't I only be finding the area between the two curves that you can now see, this piece? Great. If I wanted the other piece, wouldn't the integral be from x equals -1 to 0? And this time, which one is the highest up? Would you agree it's the black x cubed and then the green x? So, and that means then that there is a switchover. And so basically, this shape gets split into two pieces. I'm going to find the area of this piece using that formula and the area of this piece using that formula. Although in many cases, I can do a kind of cheat or a shortcut. Although this isn't to scale, would you agree that this piece is the same size as that piece? Would you get, it might not look it, but if I drew it to scale, wouldn't this piece here be the same size as this piece here? So really, couldn't I just find one of them and double it? So what you're looking at here are two different approaches to the same question. Couldn't I find this integral, which is that one, plus this integral, which is that area, and then add them up? Or couldn't I just say double this guy and get the same result? Which one do you think's got the least amount of work?
The second option.
Yeah. Don't you just need to find one thing and double it, which is easier than trying to find two things separately? Okay, so I'm going for that one then. Add 1 to the power, divide by new power. Add 1 to the power, divide by the new power. Evaluate it at x equals 0 to x equals 1. And then double it. Plug in 1, 1/2 of 1 squared, take away 1/4 of 1. That's this guy. Take away a whole load of nothings. That gets you 1/4. 2 times 1/4 gets you 1/2. So the total area between these two curves is 1/2. Any questions about that particular example? Cool. Okay. Do another example then. The area between y equals sine x and y equals cosine x from x equals 0 to x equals pi upon 2. So first thing I need really here is a graph of the situation. And I'm going to go y equals, and I'm going to do, what's the first one, sin x. And I'm going to do y equals cosine x. And since I already know it's from 0 to pi upon 2, I don't have so much to worry about, because that's going to be my x min and x max. And then I just do zoom 0, and it'll give me a pretty good picture. Okay, so now I've got something to work with. I'll try and draw a sketch on my paper, my step 1. In this case, sin x goes like this. And the other one, which is cosine x, kind of keeps going, I guess, goes something like this. And on my picture, that guy there is pi upon 2. So there's our cutoff point. And the other one is 0. So the area that between the two is actually two distinct areas, agreed? Now, I don't trust my artistic ability. That piece there might be the same size as that piece, in which case, couldn't I do the just find one and double it trick? But if I'm not 100% sure, then maybe it would be a good idea for me to separate them into two. Right. Now, step 2. Don't we have to find where these two intersect? So that means I'm going to have to solve that guy. And if normal equations with x cubes and x's are pretty awkward, I think when you add trig, doesn't it just become even more awkward? So I need to find a value of x. Actually, you know, the only one I'm interested in is the one that's somewhere between 0 and a half pi, right? I don't care about the ones that are over here, the ones that are over here. I'm only interested in one solution, somewhere in the range 0 to half pi. Any ideas how I could solve this fella? Because trig gets solved differently than, you know, x squared equals 4 gets solved. They just are. Any suggestions? One last chance. Obviously, factoring's no good. There is a trick that works quite well in some circumstances, and it's the as long as you do it to both sides, it's okay rule. So I'm going to divide both sides by cosine x. As long as there's no zeros involved, that's okay. And the right-hand side is 1. And now there is a trig identity that should be in your brain. What is sine x over the cosine x the same thing as?
Tangent.
So aren't you now just trying to find when is the tangent equal to 1? So won't that make x the inverse tangent of 1? Which is another way of saying, what angle has a tangent of 1? Does anybody know off the top of their head the one angle that I'm interested in that has a tangent that's 1? And it is in your unit circle.
45.
45.
45, which we are going to call pi over 4, right? Because we're doing radians, but you're right, 45 it is. And that kind of makes sense. If you were a gambling person, wouldn't it seem reasonable that somewhere between 0.5 and would be the answer? It seems to match the storyline. So we've drawn our picture, we've found the point of intersection, and now we're going to figure out what the area is. Now, two ways to do this one. Isn't it the area from 0 to pi upon 4, which is this piece here, and that's going to be green guy on top, take away the black guy on bottom. Do my little fella, can you see him? Green in the top, black in the bottom. Plus the integral from pi upon 4 to pi upon 2. But now it's going to be sine x, take away cosine x. And if you do the little vertical rectangle thing, can you see the sine is on the top and the cosine's on the bottom? Now that I'm looking at this, do you think I could get away with that shortcut in this particular circumstance? Do you think this plus this is the same thing as double that? That's what I'm asking. Visually, does that seem reasonable?
Yes.
Yes.
Yes. Now, if you don't feel you're 100% sure, isn't it always a good idea just to do it as two separate integrals, and that way you know you're guaranteed to be right? But if you can see some symmetry going on here, you know, where basically the shape's cut into two equal pieces, this does save a little bit of work. So it's going to be two lots of, oh, got to be careful here. Be careful, right? Antiderivative of cosine.
Sine?
You did it. Antiderivative of negative sine.
Cosine.
Cosine.
Right. Now, if you want to double check this, can't you just differentiate and see if it works? Differentiate sine, you get cosine. Differentiate cosine, you get negative sine. Do you see that work? So I know I did it correctly. Okay, so the reason I was saying be careful here is, don't, to me I found out, isn't the sine cosine antiderivative issue fraught with danger of getting the wrong sign? Now, you're going to find the sine of pi upon 4, add the cosine of pi upon 4, and then you're going to take away the sine of 0, add the cosine of 0. And the reason I wrote this down is that that isn't 0. This actually has a value. But let's do the other ones. The exact value. So you're not allowed to go and tell me it's 0.707. From your unit circle, what is the exact value for the sine of pi upon 4?
Root 2
Root
over
2.
Q.
2. So do you know that little unit circle thing that you got from Trig? You might want to go and hunt it out, you know, when you get questions involving sines and cosines and tans. Would you agree that the cosine one just happens to be the same value? Most of the time they're different from each other. And that's that guy, right? Take away, the sine of 0 is 0 and the cosine of 0 is 1. So what do I now have? I have, oh, isn't root 2 upon 2 another way of just saying a half root 2? Right, root 2 over 2 is just another way. So a half root 2 plus another half root 2, doesn't that just get you one root 2, a single root 2? Are you happy about those two adding up to give you that? Take away 1. And there's your answer. Any questions about that? You feel comfortable about the way this process is kind of working its way through? Like the, you know, the 1, 2, 3 thing? And by the way, that's step 3. Right, 1, 2, 3. Last chance I'm moving this if we don't have any issues with this question. Let me look at some homework questions. Y equals 5 over x and y equals 10 over x squared and x equals 6. We're being asked to find the area using this information. Now, if you go to your calculator and you type in those two guys, you're going to have a little bit of problem. Can you remember 141? These guys have a big problem at 0. Right. So I'm going to go and I'm going to type in the two curves and I'm going to avoid 0 in my window. So I've got 5 over x and I have 10 divided by x squared. And I'm going to go to my window and I'm going to start at 1 and I'm going to finish at 6. Now I can do zoom 0 and I might have an idea. Oops, I'm not. Start at 1. Now do zoom, which I thought I did the first time, 0. So, if we imagine this is 6, we have one of the curves that kind of goes like this, and then we have a different curve that starts here, curves down, and then goes a bit lower. That's kind of what it looks like, agreed? Now, the x equals 6 was quite helpful because it actually tells us that guy. And we're looking for the area between these two curves. So in this particular question, if I look here and here, can you see that the area that they're talking about is a very skinny banana? So the area between these two curves and x equals 6, well, x equals 6 is like a wall that they bump into. Don't I just need to know where they intersect at the other side, and that's me got my start number, right? I need a start, I need a finish. So step 1 is draw the picture. And in case we're not 100% sure, I'm going to go back into my picture and I'm going to change one of them. Do you see the 5 over x? I'm going to make that thick. So when I graph it, the thick one is 5 over x. Right, so now I know which one is which. So the one that's black, that's this guy here, is 5 over x. And the one that's green, which is basically right next door to it, is the 10 over x squared. Because it's not very easy to look at a picture sometimes on a calculator and know who's the top and the bottom guy. You're all used to that little trick in the calculator where you can make one of them thick and one of them skinny so you can tell which one's which. Right. So I'll show you what I did there. I hit y equals. I move over to the right hand side with the cursor. And then as you just hit enter, it will change what things look like. And if you hit it until it looks thick, when you graph it, 5 over x is now the thick one, and the 10 over x squared is the skinny one. So that's step 1 done. Draw the thing. Step 2. Well, don't I just need to solve when one of them is equal to the other? And every question brings its own surprises. I need to solve this equation. So we have to figure out an algebra trick technique. Any suggestions for what the next line of working would look like?
Maybe like take the reciprocals.
That might be true. I'm just not sure what you mean by that. You could
I
be
mean,
right.
like right. It is like x over 5 is equal to x squared over 10.
That's an interesting idea. Okay, what are you going to do now?
Like multiply by 5 or 10.
Multiply both sides by 5? Is that what you said?
Mm-hmm.
Huh. I just want to follow this through. So if you multiply both sides by 5, that gets you what, a half x squared? Interesting. Yeah. Okay, keep going. It's getting a bit harder, but yeah, this is some mileage. This could work. What do you want to do next?
I don't know. Maybe on the right side you could factor out an x.
Well, I wouldn't do that quite yet because that tends to lose a solution. So maybe do that, and then we'll factor out the x.
Mm-hmm.
Okay. Which means that x equals 0, or x equals, okay, what value of x makes a half x take away 1 equals 0? Because there is a nice
2.
number, 2. And that is him. And that is not how I was going to do it, but it works. So it's allowed, and it's a cool way of doing it. You want to see my way now? Just as a comparison. Cross multiply. Remember cross multiply. Subtract 10x from both sides. Factor out a 5x. And there's the same two solutions that you just got. So one of the cool things about math is if the method is valid, it will get you the right solution. And there could be 2 quite different approaches, maybe 3 sometimes, to coming up with that solution. But the bottom line is, isn't it the same solution? That's what's important. Now, when you look at this picture, can you see that you're only interested in from 2 to 6?
I have a question about that.
Yes.
So at least in the example where you use sine and cosine, we had a left and a right limit.
Yes.
This one, like, how do we know not to do anything to the left of 2?
How do we, okay.
Yeah, like, why are we not getting the area in between?
Oh, here?
Yeah, that.
Because this shape actually shoots all, that's actually just 1. Shouldn't have put that as a solid line. The y-axis is actually over here. That's at 1. That's where my window is.
Oh,
This shape does this horrible thing,
got it.
right? So that 1 there probably shouldn't have been a solid line at all, because it's not, you know, this is the piece we're looking for, essentially. Now, for the area in this particular question, isn't it really just 1 area? I don't need to have 2 pieces. And if I put my little tiny little, and it is almost not negligible, rectangle, can you see it's the black guy on top? And the black guy was 5 over x, and it's 10 over x squared on the bottom. But would you agree that there's no crossover there, so it's just a single area this time? Well, this is going to be fun. I'm turning 10 over x squared into 10x to the negative 2, and the reason I'm doing that is so that I can do the power rule for integration. On the other hand, I'm not turning the 5 over x into 5x to negative 1, because isn't the antiderivative of 5 over x a log? It's not a power rule question. So we are now going to do the antiderivative of that guy, which is 5 log x, and this guy, you add 1 to the power and divide by the new power. And you're going to evaluate that at 2 to 6. And I'm going to change that a little bit before I start working on it. So plug in 6. 5 log 6 plus 10 over 6. Take away 5 log 2 plus 10 over 2. Why do you think I went to all the extra work of changing this guy into that form? Why was it necessary to turn this guy into that form?
Make it pretty rule thing.
Yeah, it's a style. You call it the pretty rule thing. That's a good name for it too. I call it a style point, right? It's got to look pretty. You're right. Plus, isn't it much easier to figure out what 10 over 6 is than 10 times 6 to the negative 1 power? I mean, in your brain, isn't 10 times 6 to the negative 1 just, what the heck is that, right? Now, that becomes 5 log 6. That guy becomes 5/3. Take away 5 log 2s, and that's take away 5. Now we have some different style points. Oops, not a plus. 5/3 take away 5. 5/3 take away 15/3 leaves you with negative 10/3. Now, as style points go, that might look good. I did notice, unfortunately, some of you in the test would turn this into decimals. Decimals will lose you points. Decimals are no good. Exact values have to be used. So that's why this is a bit harder. If this was just a decimal, I could probably have stopped up here and just hit buttons on my calculator and said 1.2345 or whatever. But now we have to do some work here. Is there anything algebraically that you can do to that guy that might help?
you could, using the quotient rule, write it as 5 natural log of 6 divided by 2.
So essentially, and I'm putting an extra line in, but what you said was exactly true. You pull out a 5, and then 6 divided by 2. And so you get that guy. And that is the end of the line. Okay, everybody, will you say hi? And that way I'll take attendance.